Today we're going to talk about momentum and conservation. This is chapter 9 in your textbook. So a couple things I want to remind you guys about. Newton's second law, this is pretty key, and so we're going to use this again. And so I just wanted to give it to you guys here to remind you again, force is measured in newtons, which I know you guys know, and that your acceleration depends on your force and your mass. This is going to be really important when we start talking about momentum. One of the important key concepts in this chapter is impulse. And impulse is your force multiplied by your time. We're going to do impulse is measured in newtons per second, and we're going to be able to figure out the impulse of a baseball or a car or any sort of crash. And so this will be kind of important. But you just need to know that impulse is equal to force times the time. Now, momentum is our big equation in this chapter. It's not super difficult, but it is important. So momentum is measured in kilograms per meters per second, so it doesn't have a really nice unit, which is kind of sad. And then momentum, for some reason, is this little P, and it's actually not an American P, it's a Greek letter. But it looks like a P, so you can just draw a P, and it's just your mass times your velocity. And so we use P for momentum, which is kind of confusing, but make sure you get that straight in your heads. The impulse momentum theorem, this means that impulse, that force times distance that we talked about earlier, that means that is equal to your change in momentum, or your final momentum minus your initial. So momentum is mass times velocity, so it would be your mass times your final velocity minus your mass and your initial velocity. Okay, this is kind of what goes on when we talk about airbags. Airbags reduce the force on you by hitting the steering wheel, by exerting the force over a larger area, that big giant airbag, and reducing your likelihood of injuries. And so this is really some key concepts when we're talking about car crashes and things like that. Okay, now let's try and solve this problem. A 22 kilogram vehicle, and it is traveling at 94 kilometers per hour, but we're going to use meters per second. They've already converted it for you, which is really nice. Traveling at 26 meters per second can be stopped in 21 seconds by gently applying the brakes. Then they say it can be stopped in 3.8 seconds if the driver slams on the brakes. And then in 0.22, less than a second, if it hits a concrete wall. What average force is exerted on the vehicle when the driver gently applies the brakes? So let's talk about the things that we know. We have a mass, and it's equal to 2,200 kilograms. Okay, of 26 meters per second. And then we'll just do the one with the gently applying the brakes. And then we'll do the rest in a different slide so we can fit it all. And then, and so we're going to do the time for gently applying the brakes, and that's going to be 21 seconds. Okay, we're going to have a formula. Okay, we have a couple formulas that we've learned. We know P, or momentum, is equal to mass times velocity. And then we have that impulse momentum theorem, saying that the impulse is equal to the final momentum minus the initial. So let's see what we've got here. First thing we need to do is we need to find our initial momentum and our final momentum. So that'll be the first thing we do, is find our initial. And it's in kilograms times meters per second. I'll try and make this, maybe that looks a little more like a multiply for you guys. So our initial is equal to our mass times our initial velocity. Okay, and that's just going to be 2200 times our initial speed, which was 26. Okay, and then we'll just multiply those guys together, and we'll get a really big number, and that's okay, with our weird units, kilograms times meters per second. Okay, now that we've found that, we need to find our final momentum, and that's going to be momentum with an F. Again, it's going to have those weird units. And so we'll do our final mass times our final velocity. And remember, we're stopped at the end, right? Because the cars are stopped moving. And so his final velocity is 0, which anything multiplied by 0 is 0. So we're going to get a final momentum of 0. Okay? So now that we've got that, we can use our impulse momentum theorem, and I'm going to switch to this other side just so I'm going to move this up a little bit if I can. Actually, I guess and then we've got a little bit of space right here. So we'll see if we can fit it. So we're going to use our impulse momentum theorem. Okay, I'm going to use a different color for you guys. So we'll have our force is equal to, our momentum is equal to our final minus our initial. Okay, so we can take both sides, divide them by the change in time. And then we can go ahead and plug in our numbers, and that'll give us our force. So we'll have our final momentum, which is 0, minus our initial, which is 57,200 kilograms meters per second, and we'll divide by our time. So you're going to get a negative number, that's okay. And it'll be in newtons because we're doing a force. Okay, so this is how you can find the force exerted on the driver when he's just braking gently. Okay, so a couple things you'll want to keep on your paper because we'll need them later. This is 57,200 and this 0. And then of course your mass up here. So let's go to the next slide, see a couple of things. So let's go ahead and write those things down that we got last time. We know our final momentum is 0. And we know our initial momentum is 57,200. And we have our mass still. And then we have our change in time, which is going to be 3.8 seconds. Okay, we can use the same formula that we found on the last one, where we take our force is equal to our final momentum minus our initial and divided by our change in t. Okay, we can plug that stuff in. And you can see as your t gets smaller, your force is going to get bigger and bigger, which is why the slower or the less the more you can slow down, or the more time it takes for you to slow down, you're not going to be going as fast when you hit the wall or wherever you're doing, and so you're less likely to get hurt. Remember, we've got that law of inertia, that an object in motion stays in motion unless acted on by an outside force. So this is a pretty big force, right? This is 15,000 newtons. If you're slamming on the brakes, this isn't even like hitting the brick wall yet. So you can see it's increasing. Now let's do the last one. Now we're going to do when we hit the concrete wall. Our mass is 2,200 still. Our initial momentum is 57,200. Again with the weird units. Kilograms times meters per second. Our final momentum is 0 because we're not moving at all at the end. And now our time is going to be less than a second. And this is why if you hit a brick wall going full speed, it's going to hurt. We use the same formula. Our final momentum minus our initial divided by our change in time. And we'll take our final momentum, which is 0 again, divided by 57,200. And we use 0.22 for our time. And you can see our force is going to be huge. 260,000 newtons. Okay, so there we go. We did momentum, and we did impulse, and we did the impulse momentum theorem. So that's kind of what we learned today in this video.